So I wrote here, you got a copy? We're good? I wrote here orbital, or I call it cosmic potential energy, and I start out with a question. We can't use potential energy equals mgh in outer space. Why not? Zach? Yeah, there is. I could measure that quite easily. That's not the issue. Why can't we use mgh in outer space? Chang, what? The further you go into space, the less this gets. So we cannot use mgh. So from now on, whenever we're doing energy questions, one of the first things, Josh, we have to ask is, are we cosmic in space or not? We need a new equation for conservation of energy. We need to do some review. Recall, the area underneath a force versus distance graph was equal to what? No. And then kind of sketch a line going kind of up slanty a little bit like that. What was the trick that I taught you? If it's area, how could you figure out what it meant? What did you do? So what is force times distance? What? Work. Except now I'm going to be even more specific. So on this little sketch of a graph, I'd like you right here to make a little point and call it point A. Eyeball it roughly. And right here, make a little hash mark and call it point B, roughly. And so draw a little vertical dotted line, draw a little vertical dotted line, and kind of do that to signify that that's the area we're talking about. Now I'm going to say this. It isn't just work. The area is the work, and you can put in brackets energy, required to move an object from A to B. That's how much energy, how much work it took to move this mystery object of which I don't know, but I can tell you it took that much energy, that much work to move it from location A to location B. And I'm not going to be more specific than that. Why does the force get bigger? I don't know, but I'm just saying that's a better way to think about this area underneath a force versus distance graph. Question, Linnea? You okay? For force of gravity versus, instead of distance, we're going to use the letter R. So now let's put Fg and R. The graph is not going to be a nice straight line. I can do a force versus distance graph. The equation for gravity, don't write this down, is this. Don't write this down. Big G, big M, little m over R squared. What I really want you to notice, you can write this down if you want to. You can say the force of gravity is proportional to 1 over R squared. There's other stuff there too, but the R is on the bottom and it's squared. Pre-Calc 12 students, it's a reciprocal of a parabola. Because squared is a parabola, but it's on the bottom. It's going to look kind of, I'm not going to be fussy about scale, but that graph would look something like this. It's a curvy graph. Which makes sense, because as you go further and further away from the planet, as R increases, what happens to the force of gravity? Bigger, smaller, or stays the same? Gets smaller. Doesn't get smaller in a linear manner, though. Remember, twice as far meant 4 times weaker, 3 times as far meant 9 times weaker. So it should be curvy. Let's be even more specific. So we're going to re-sketch this same graph. Fg, put an R there, and sketch that shape. But now we're going to be just a little more specific. Again, we're going to put a hash mark right about there. but we're going to call this our Earth. So 0 on the y-axis would be the center of the Earth. Here is how far we are from the center of the Earth. So this distance here, IRA, is 6.38 times 10 to the Earth surface. And let's put another hash mark here. Let's call it R final. It could be an orbital radius, or if we're not in orbit, we're just moving a certain distance away. And again, let's draw a little dotted line, and again kind of show that this is the area that we're talking about. And what kind of a graph is this? What versus what? What's on the y-axis? Force of gravity. Gravity, that's on the y-axis. What's on the x-axis? So this is a force versus distance graph. What does the area tell me? Work, but now I'm going to be even more specific. The area here is the work. What word am I going to put in brackets, folks? Energy required to lift an object from our Earth to our final. And you'll notice, Ange, it's not a straight line, it's a curve, and this is why we can't use MGH. Problem. Here, we could find the area. We said this was a trapezoid, and we always broke it up into a triangle and a rectangle. Great. What's the area of that? Now, who's in calculus here? You will learn towards the end of the calculus course a method for finding the area under a curve. Currently, you're learning how to find the slope of a curve. We call it the derivative. Calculus was invented for two things: find the slope of curves and find the areas under curves. You'll have to learn a different mathematical procedure, but you'll learn how to find the area under a curve. You don't know that right now. So I'm going to have to do a little fake hand waving to generate this equation. The best way to generate this equation would be to do something called integration, starting with the force equation, and you get the work-energy equation. So here's what I'm going to say. Since work equals force times distance, we can say potential energy, this is going to be cosmic potential energy, is equal to which force when you were lifting something? When you were lifting something, which force was it? But now we're going to use Newton's universal gravity, big G, big M, little m, over r squared, times, and I guess, Tato, we're calling the distance r. Oh! What do we notice? One of the r's cancels. And this is the potential energy equation, but listen. Leave a small space after the equal sign. It looks like this. The potential energy, cosmic potential energy, leave a space, is big G, big M, little m, over r. Except, look up. There's a negative. I forgot to put a box in my notes, but this would be in a box. And you know what all of these symbols means. What's big G? That's Newton's universal gravitational constant, 6.67 times 10 to the negative 11. That's what we have to put there to get our answers into newtons or joules or whatever. Big M, mass of the planet. Little m, mass of whatever you're lifting. R, how far you are from the center of the planet. Y negative. Who's in calculus? Because if you take the derivative of this with respect to r, you'll get force. I can give you that explanation. But my Block D Physics 12 class has no calculus students because that's your calculus class. So I have to give you another explanation. Y negative. Okay? It does come out of the math. because you'd move the r to the top and make it r to the -1, and the -1 would move to the front, and you already have a negative there, and you have a minus would cancel with the minus, you get a positive, and you'd subtract 1 from the exponent, you'll get an r to the -2, move back to the bottom, you get your r squared. Did I go too fast? You guys have done those ones. Hopefully you're fairly good at those ones by now. There's another reason it has to be negative. We're going to define zero potential energy as the situation when you won't fall anymore. If you won't fall when we let you go, you have no potential energy. And where is that? That's out at the very edge of the universe. In fact, we say relative out to infinity. If you went to the edge of the universe so that you were infinitely away from any planets, how much gravity would there be? Zero. So will you fall if we let you go? So do you have any potential energy? So the phrase we use is relative to zero at infinity. So out at infinity, how much potential energy do you have? Zero. If you're closer than infinity, you must have less potential energy because you would have to add energy, do work, burn fuel to get there. What numbers are less than zero? Okay. So I wrote here this. Why negative? Negative because F is the derivative of PE. So I can use that for you as calculus students, and that gives us a positive form. Or here's the paragraph I'm going to give to my non-calculus students. Out at infinity, at the edge of the universe, an object would have zero potential energy because it's not being affected by any gravitational field. It can't fall anywhere. If our height is less than infinity, well, we have less potential energy. What numbers are less than zero? Answer? So we use the phrase relative to zero at infinity. In fact, sometimes in the homework, you'll see it abbreviated as relative to zero at infinity. If you ever see that phrase in the question, that's my way of telling you, please make sure you use the cosmic potential energy equation, not MGH. And rule of thumb, Brian, if you're in space, use the cosmic one. So, what can we now handle? 3,400 kilogram mass is released from a height of 6,300 kilometers above the Earth. How fast will it be going when it hits the ground if we ignore air resistance? Okay. Is there a change in height? Yeah? Is there going to be a change in speed? Will it speed up as it falls? Yeah. So is there a change in height? Is there a change in speed? Is there a yucky curvy force? This is a job for conservation of energy. So we're going to start out same way we did in our work and energy unit. We're going to start out by going PE initial plus KE initial equals PE final plus KE final. I should have done something else first, by the way, before I even started. 6,300 kilometers, nice try. I should have said 6,300 times, Mr. Dewick? 1,000. 6.3 times 10 to the 6th. I'm going to cross this out right now and replace it with 6.3 times 10 to the 6th meters. I do that anytime I see yucky units just so that I don't foolishly later on when I'm in a rush plug in the wrong thing. Okay. Where is initial? Out in space. So we cannot use MGH. For this entire question, we cannot use MGH. Are we starting out in space, Alec? Then we have to go cosmic. So potential energy initial is going to be negative big G, big M, little m, over R initial. What's my initial kinetic energy? If we're releasing it, how fast were we going at the beginning? Hey, we can cross that out. That's good. Equals. My final potential energy is not 0. Wait a minute, Mr. Dewick. We're on the Earth. Where is 0 in cosmic potential energy? Out at? No. Where is 0? Out at? The only time you'll have no potential energy is if the question says, imagine you're going to the edge of the universe. That will be a 0. Are we using cosmic potential energy? Yes. So we have to go with negative big G, big M, little m over our final. Plus, kinetic energy is not going to change. What's kinetic energy? Still, half mv squared. And that's the v they want me to find. This, yeah? Doesn't matter. The whole fraction is negative if you want to do it that way, but you can think of it, the top is going to be negative. Yeah. Okay. One thing I do notice is it turns out the speed that an asteroid hits the Earth at doesn't depend on its mass. Yes? The damage it does very much, Paige, depends on its mass. But a little tiny asteroid and a stadium-sized asteroid, they're both going to hit the Earth with the same speed. It's just a little bit more damage. This is around where my love for getting things by itself dies. I am not going to try and get the V by itself. Instead, what I'm going to do is get this whole thing, don't circle it, I will, by itself. I'm going to plus this to that side. You can draw a little arrow there. So I'm going to get this. The negative big G, big M over R initial drops down like a domino. And I have now a plus. This is why I said, Tad, it really doesn't matter. I just treat it as minuses and pluses. Big G, big M over R final. And R final is going to be the radius of the Earth. It's going to be the 6.38 times 10 to the 6th, because that's where we're stopping. That equals a half V final squared. What I'm going to do is I'm going to get that as a number. I'm going to crunch that, and then I'll times by 2 and square root. I mean, you can try and get the V by itself. It's just, Zach, not worth it right now. Okay. We're going to have to do some fairly heavy-duty typing. Ready? Negative. What's big G? Big M. Are we Earth? Okay, so. Now, what's our initial radius? That's 6,300 kilometers. Was that a radius or an altitude? Okay, so my initial radius is going to be 6.3 times 10 to the 6th plus the radius of the Earth. Yes? Stop writing once you've written that. This is where we're going to try and be a little bit clever and save ourselves some typing and some blisters. What letter is that right there? Capital? 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 Are you saying that those are all the same? Plus ditto mark times ditto mark. I'm serious. Divided by, is the bottom the same? No. What's our final? Surface of the Earth, which is just going to be 6.38 times 10 to the 6th. That equals 0.5, or heck, a half. You know what? That equals V squared over 2. It's a half V squared. I'm going to give you some advice here. Everybody get your calculator out and don't work ahead. Don't work ahead. Have I gone on the occasional calculator rant? Yeah. Okay, so I'm going to make the assumption that all of you have a calculator that will let you backspace edit, and bring back the previous lines. Here's what we're going to do. We're going to type in only the first fraction. Negative 6, negative, Mr. Duick, negative 6.67. Hit your scientific notation button, wherever it is, negative 11, times 5.98. Hit your scientific notation button, 24, divided by, I have to put the bottom in brackets, 6.3, scientific notation button 6, plus 6.38, scientific notation button 6. And stop typing once you've typed the first fraction. And you'd hit enter. I got a negative. Don't freak out. The negatives and positives, as long as you're careful with the numbers, they will all take care of themselves. If we want our final answer to be positive, it will work out that way. Do you get negative 314,563? That there? Okay. I'm going to write down about 5 sig figs worth. So I'm going to go negative 3.1456 times 10 to the 1, 2, 3, 4, 5, 6, 7. Negative 3 point, what did I say it was? 1456. And then I'm going to write a plus sign. Everybody get that okay? Josh, you got that okay? Now, on your calculator, since I noticed that the second fraction is almost identical, why don't I just backspace and do a little editing? For example, it seems to me that I can just delete the negative in front. So I will. So I will. And then it seems to me on the bottom, all I need to do is delete the 6.3 times 10 to the 6th and the plus sign, and I have that second fraction. I strongly encourage you to do this because you're going to be doing so much typing, Kieran. If you just make sure you do the first fraction very, very carefully, and then backspace and edit, you'll cut down on typos. You really will. The second fraction works out to positive 6251818. That. I'm going to write down about 5 sig figs worth, 6.25182 times 10 to the 1, 2, 3, 4, 5, 6, 7. That equals v squared over 2. Conveniently, I have this number sitting on my calculator. I'm just going to now add the negative or subtract this number. So plus negative 3.1456, scientific notation button 7. And I am rapidly running out of room, so I got to go up here. Sorry? Yeah, I wasn't kidding when I told you these are going to be big questions. Sorry. Write small. By the way, this is nowhere near the longest question you're going to be doing today. And I get, now I'm only going to write a couple of, because I have this start on my calculator, I'll write 3 sig figs worth, 3.11 times 10 to the 1, 2, 3, 4, 5, 6, 7. So I get positive 3.11 times 10 to the 7th equals v squared over 2. How will I get the v by itself? Now. And then, I'm not even going to show that step, I'm just going to do it. Times by 2, square root of that. And that looks like a pretty good answer. Asteroids hit pretty fast, 7,880 meters per second. This is the cosmic potential energy equation. It actually is exactly the same physics as dropping an object here on the Earth, but because here on the Earth, if you're moving through this much distance, g is still 9.8 or close enough to it, we can use the MGH shortcut. Can't do it when we go cosmic. Yeah, turn the page. Jaden, what's example 2 want me to find?
Word.
How much what? No pun intended, it's going to take a lot of work. This is not the longest question, but this will be close to the longest question. The longest question is calculating how much work to get something into orbit. Now, let's read this together. It says this: how much work is done in lifting a 1,200 kilogram satellite from the surface of the Earth to a height, I'm going to underline the word height, of 1.2 times 10 to the 7th. This will not get it in orbit. All we're doing is lifting it there. As soon as you let go, what's it going to do? Come crashing down. Because to stay in orbit, we would also need to give it kinetic energy to get it to circle the Earth. We're not doing that yet. Someone had a question. Did I answer it? Your hand was going on? Okay. Jaden, what's this question asked me to find? Why can't I use force times distance? Because the force of gravity, what? As you go further from it, changes. So we're going to have to use work equals, I think this time I gave you a whole half page, yeah? Change in potential plus change in kinetic. Because all we're doing right now is asking, by the way, instead of how much work, how much rocket fuel, and all we're calculating is how much rocket fuel to get it to the right height. We haven't actually then calculated how much rocket fuel needed to give it the kinetic energy to stay in orbit. All we're calculating right now is how much work, how much energy, how much rocket fuel to get it up there. Because it's lifting and we're not staying in orbit, we're going to assume we start and end at rest. This is not correct, by the way. Is the Earth at rest? So if you want to get a little boost of kinetic energy, you want to launch where the Earth is spinning faster. In fact, the best place to launch would be from the equator. One of the reasons Elon Musk is trying to do landing on ships, he also wants to do launching from ships. If you launch from the equator, you get a huge kinetic energy boost from the spin of the Earth. You launch in the same direction as Earth's spin. One of the reasons that the Russians had such a tough time with their space program is they're very far north. Even to this day, Russian rockets are workhorses. They have to be. Where did the U.S. launch from? Florida, as far south as they could go. Yeah. Further south you go, the closer to the equator you go, the more kinetic energy you have. So what I'm going to say is, Sharon, to keep the math nice, we're always going to assume that we're working for Superman at his Fortress of Solitude at the North Pole. And so there is no extra kinetic energy boost there, because right at the North Pole, the Earth is really not spinning at all. Okay? Jaden, what's changing anything? Don't write this down, don't write this down, don't write this down, don't write this down. Why can't I do that? Yeah, we're going cosmic. So we're going to use our new potential energy equation. Negative big G, big M, little m over, and what's changing is R. So R final minus negative big G, big M, little m over R initial. Going back to Tato's question earlier, see the minus minus, it's going to become a, yeah, I don't really freak out about whether the whole fraction is there, whatever. There's a negative kicking around. All right. Are any of these zero? Aren't we zero on the... No, where are we zero if we're using this equation? Way out at infinity. Okay. Golly. Plug and chug. Negative. Jaden, what's big G? What's big M? What's little m? 1200. Oh, I should have asked, Jaden, does the little m cancel here? Is there an m in the... No. And you know what? That does make sense. Here it shouldn't cancel. It should take more rocket fuel to put a bigger satellite up there. All over. Now, what's our final? What word did I underline in the question? No, what word did I underline in the question? Height. So I think our final is the radius of the Earth plus that extra height. Is that okay? What's a minus minus the same as, Jaden? Are you positive? Shut up. Okay. Now, look up, look up. What letter? Look up, look up. What letter? U. What letter? What letter? What letter? What letter? What letter? You know what? Ditto mark times ditto mark times ditto mark. And I'm doing that because that's what I'm also going to do on my calculator. That second fraction, I'm just going to backspace, edit, and just tweak whatever I need to tweak. Way less typing. Over. What's our initial? Where are we starting? The surface of the... So I'm going to put 6.38 times 10 to the 6. Get your calculators out. I'll clear my screen. The first fraction, negative 6.67 times 10 to the negative 11 times 5.98. 98, Mr. Duick. Boy, this is times 10 to the 24th times 1200 divided by bracket 6.38 scientific notation 6 plus 1.2 scientific notation 7. Do y'all get negative? Is that right? I think I made a typo. You know what? I missed a decimal. I missed a decimal. Patience, grasshopper. It's 1.2. That. Okay. You're going to find more often than not, if I'm giving you good numbers, your energies will be in the 10 to the 9th, 10 to the 10th, occasionally 10 to the 11th range. So I'm going to go negative 2.6041. That's 5 sig figs times 10 to the 10th. Plus. Bring the previous calculation back. If you don't know how to do that, you'll need to see me and we'll sit down with your calculator and figure it out. Sarah, did that work okay? Oh, okay. I thought you were giving me a squinty eye. Delete the negative. And I guess I just have to delete the plus 1.2 times 10 to the 7th. Way less typing. My initial potential energy is positive 7.5022 times 10 to the 10th. And now I'm good. I have this number stored on my calculator. So I'm just going to add this. You can either add the negative or you can just go minus. I'm lazy, so I just go take away 2.6041 scientific notation 10. How much energy, how much work would it take to get this satellite that high? That much. Oh, and if you told me how much energy per joule I could get from, sorry, how many joules per liter I could get from the rocket fuel, I can tell you how many liters of rocket fuel I need. Of course, in real life then, once I add the rocket fuel, I've just changed the mass. So now I need to resolve this and figure out how much energy I now need. Oh, but once I get that new answer, that means I'm going to need to add more rocket fuel, which means I've now just changed the mass. So now I need to resolve it to see how much more fuel. It's expensive to go into outer space. Do y'all get 4.90 or 4.90 times 10 to the 10th? Is that right, folks? And it's work, so it's joules. That's a lot. Oh, and as I wrote here at the bottom, Chang, this satellite has no kinetic energy. All we've done is figure out how much work to get it to the right height. It's going to come crashing back down right now. As soon as we burn up our fuel, it's coming back down and hitting the Earth pretty fast. To lift an object, and that's the word that I also underlined, Jaden, we only need to give it potential energy. To put an object in a stable orbit, we need to give it both potential energy and here it is. I like example 2. I like example... No, sorry. I sort of like example 2, except in example 2, I gave you the orbital speed. Later on, I won't be giving you that. I'll make you calculate it. We can handle this. Sharon, what's example 2 want me to find? It's going to take a lot of work. Work what? So here's the key phrase. Can you all look up? We're putting it into a stable orbit. Sharon, what does it want me to find? Can I use force times distance? Why not? Because the force of gravity does what as I go further and further? It's changing, and I can't. Force times distance only works for a constant force. So we're going to have to use our better definition of work, that it's the change in potential plus the change in kinetic. And Sharon, this time, because we're in orbit, there is going to be a change in potential. There is going to be a change in kinetic. I recommend finding each of those separately. What do you want to find first, the change in potential or the change in kinetic? You can pick. Change in potential? Okay. So I usually go like this, kind of draw a little line, and then I'm going to say, all right, change in potential. What's change in anything? Right? Pause. Can I use MGH, or are we cosmic in outer space here? Okay, so it's going to be our new potential energy equation. Negative big G, big M, little m over our final, minus negative big G, big M, little m over our initial. There's my final minus initial. Ugh. There is a little minus in the middle, which is going to become a. We'll get that in a second. All right, time for numbers. The change in potential energy is going to be negative 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. What's little m? 925? Divided by... What's our final? Sharon, my angel. Is that a radius? Say yes. Is that a radius? Okay, so do I need to add the radius of the Earth to that one? No. In the previous ones, I gave you the altitude, which is measured from the surface of the Earth. And so to get the radius, I have to add the radius of the Earth. Here, I did not. So read very carefully whether I give you a height or altitude, or whether I give you a radius. So I can just go 2.6 times 10 to the 7th. And then you said plus. And then, Sharon, I'm literally going to go ditto mark times ditto mark times ditto mark. Divided by our initial surface of the Earth. If the question doesn't say Earth, assume it's Earth. I think we're assuming it's Earth. 6.38 times 10 to the 6th. All right. Negative 6.67. Scientific note. By the way, ready for a clever trick? Look up, look up, look up. If you can go back several lines on your calculator, you may notice you have a line that has the 6.67 times 10 to the negative 11 and the 5.98 times 10 to the 24th, and you can just start typing after that and save yourself a little bit of effort. 925 divided by 2.6 times 10 to the 7th, and delete any extra characters. Tricks of the trade. I've gone on my rant about getting a good calculator yet. Oh, this, by the way, this is the unit I had in mind last year in Physics 11 when I was yelling at all of you to get a decent calculator. For the final potential energy, oh, I forgot the negative. Oh, I can just put a negative in front. Do you get negative 1.419 times 10 to the 10th? Okay. negative. I forgot to put the negative on my calculator, but that's easy enough to rectify. Negative 1.419 times 10 to the 10th, and then there's a plus sign. Ditto mark, ditto mark, ditto mark. I would delete the negative, except I forgot to type the negative in the first place. In fact, I think all I need to change is 6.38 times 10 to the 6th. My initial potential energy, 5.7829. It's actually negative 5.7829, but it's a minus minus, which becomes a plus. So my initial potential energy is negative, but 5.7829 times 10 to the 10th. And now I can combine those. How much work does it take just to get the rocket to the correct height or radius? How much work am I doing just in changing the potential energy? Do you get 4.3639 times 10 to the 10th? Or am I wrong? If I'm wrong, let me know, because it's easy to make typos here. Is that, yeah? 4.3639? Bang on. Sharon, that's the change in potential. Put a box around it because we're going to want to find it later. So all we found, Sharon, is that. What else do we need to find? I draw the line. I'll change colors. What's changing anything? You starting to see why I bring all these already in Physics 11? Did you say final minus initial? And kinetic energy is not going to change, so it's going to be a half mv final squared minus a half mv initial squared. Are any of these zero? We've said that we're going to assume that we're launching for Superman, that we're launching from the Fortress of Solitude at the North Pole. So we're going to, just to keep the math nice, we'll let the initial be zero. But you can see it actually would be a big advantage to launch from further south so that your initial was whatever speed the Earth was spinning at. That saves you some rocket fuel. 0.5. What was M? 925? And what's V? And this final would be V orbit. 3,917 squared. What if I hadn't given you that speed? Gravity is what's pulling you in a circle. And you can calculate the orbital speed because you know the radius. And then you can find the kinetic energy. And that's what I'm going to ask you to do on the test. Sorry. And I get the change in kinetic equals a half m 3917 squared. 7.0961 times 10 to the 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. 7.096 times 10 to the 9. How do I find how much work? Work is the change in potential plus the change in kinetic. Those two numbers in the box, I'm going to add them together. If you did this in your homework without showing this next step, going straight to your calculator, that's fine. In our notes, though, let's write down that that's what we've done. So now let's say work is going to be change in potential plus change in kinetic Conveniently, I have this second number stored on my calculator, so I'm going to go 4.3639 times 10 to the 10th plus, answer button. you'll notice I get a positive answer, which I should, because I will have to add fuel, burn fuel. So even though we defined 0 out at infinity, Tado, this is why I said if you relax all the numbers, as long as you're careful with the signs, they'll take care of themselves. You get 5.07 times 10 to the 10th joules? No, yes? Yes? It's a lot of work. No pun intended. Yeah, Sharon yawns afterwards. She's tired. Took it out of you, didn't it?